We are going to take a look at chapter 6, which is all about rational numbers and proportional reasoning. Now, the objectives in chapter 6, I want to point this out. These are overall overarching objectives. So, this is not a lesson plan objective. This is a lesson plan for a big idea or a chapter, which is why we can say students will be able to understand and explain, even though that's not really measurable. That's our big idea. We would then break these objectives down into singular objectives that are measurable at the lesson plan format. So this is what we're going to be looking at today. And first, we're going to start with some definitions. The beginning of chapter 6 is really about orienting yourself to some key definitions. So first, let's talk about a numerator and a denominator. A numerator and a denominator are used in a fraction to show the ratio between two values. Rational numbers are related to this because a rational number is any number that can be represented as a fraction. So rational numbers use division or fraction problems. They could also be a solution to a multiplication problem because even a whole number like 6 can be written as 6 over 1, which means it's rational. It can be used as a part of a whole. It can be used as a ratio, and it could even be used in probability. Here are some different examples of rational number models. Now, each model has a different context. The area model is going to be great if I want to divide an item into equal parts. That's when the area model is really useful. The number line model is useful when we're trying to compare fractional amounts. And then the set model is useful when we have an object, like we're taking in books, and we're going to divide books into equal parts of boxes. So we're not necessarily cutting one object into pieces, but we're splitting up a group of objects. So to really grasp this, we want to reframe how students think about fractions. We want to start thinking about fractions as parts of a whole in a model. And to do that, we must consider that there's a whole being considered here. There's some whole portion or big thing that we're looking at. The number b in the fraction, the denominator, is the equal sized parts that we divided this whole thing into. And then A is going to be the number of those parts that are selected. So if I have 2 slices of pizza out of 8, 2 is going to be the number that was selected. 8 is going to be the equal size slices that I sliced the pizza in, and the whole is going to be the pizza. So a proper fraction is a fraction where the numerator is smaller than the denominator. That's all this means. We have started moving away from proper fractions to some degree, but it's still a vocabulary word we want students to know. And improper fraction is when the numerator is larger than the denominator. So we're kind of teaching these as categories. So if I look at a fraction, I should know if it's proper or improper. The number line is used a lot of times with measurement. So when I'm using a ruler or some other function of measurement, and I can use these dots on the number line to help them measure quantities. Now, obviously, I'm not going to measure a negative value. That's not what we're trying to do there. But over here on the right-hand side, I can show them, hey, this is 1, 2, 3 out of 4. So it's 3/4 of the way to 1. So this kind of helps us when we're dividing into quarters or even tenths a lot of times with these measurements. Now, equivalent fractions are fractions that represent the same value on the number line. So this means that I could take an existing fraction and multiply it by the exact same value at the top and the bottom, and that would give me my new fraction. And but they would be equivalent because they really mean the same thing. So if you look at 1/3, the area shaded is the same as 2/6 and the same as 4/12. You should notice that when I multiply 1/3 by 2 over 2, that gives me 2/6. Fraction strips are excellent for teaching equivalent fractions. So this is a place where we can really start looking at, well, look at this, 3/6 is the same measure as 1/2. So these are great ways to show equivalent fractions before we start launching into the more abstract idea that they're going to be fractions where we're multiplying by some number. So in this slide, the fundamental law of fractions is just saying if I multiply the top and the bottom by the same number, they're equivalent fractions, just like we saw with 1/3 and 2/6. They're equivalent fractions because I multiply the top and the bottom by 2. Here's an example of this. I know these are equivalent fractions. I know that I'm multiplying 12 and 42 by something to get the second fraction because they're set equal to one another. So I'm going to think about, what do I multiply 42 by to get 210? And if I don't know that, I can do 210 divided by 42, and that gives me 5. If I multiply the denominator by 5, in order for them to be equivalent fractions, I have to also multiply the numerator by 5. So I get 12 times 5, which is 60. So the value of x is 60. Simplifying fractions is taking this process and working backwards from this process. Instead of multiplying by something, I want to divide the top and the bottom by the same factor. So if I want to simplify 28 over 42, I'm going to say, what is 28 divisible by that 42 is also divisible by? So if I look at 28, and if I want to know the largest number it's also going to be divisible by, that would be 14. So I could do 28 divided by 14, and that's 2, and 42 divided by 14 is going to be 3, so I get 2/3, and then the b squared and the b squared completely cancel out, and my a at the top cancels out, and I'm left with 1 in the bottom. In part B, I can factor a 3 out of the denominator, so I get 3 times a plus b, and then I can cancel out the a plus b's. Now you'll notice I'm also saying where a plus b is not equal to 0, because we have to limit the domain. Anything that would make the denominator of the rational expression 0 has to be omitted. In part C, I can factor out an x in the numerator and get x times x plus 1. Then my x plus 1's cancel, and so it simplifies to just x, but I still have to add that qualifier that x cannot be equal to -1. In part D, this is as far as I can go. There's nothing that can be divided into both the numerator and the denominator. There's no factoring work that I could do here so that I would be able to cancel something out. If we look in part E, I can factor a 3 out of the numerator, and then I can cancel the 3 in the top and the bottom. If I look at part F, you have to remember that is this difference of squares. So it factors to a plus b times a minus b, and then the a minus b's will cancel out. And in part G, that is as far as it can go. There's nothing that can factor a squared plus b squared. If I want to show the equality of fractions, there's a couple of different approaches I can take. The method that I choose most of the time is just to reduce the fraction as low as I can. So if I take 12 over 42 and I reduce that as low as possible, I get 2 over 7. If I take 10 over 35 and I reduce that, the lowest possible value I can get is 2 over 7. Because the simplest forms are the same, they are also equivalent fractions. Now in method 2, I could rewrite both fractions with the same least common denominator. So I'm taking a different approach. The least common denominator would be 210 for the factors of 42 and 35. And when I get that common denominator, remember what I have multiplied the bottom by, I have to multiply the top by. I get 60 over 210, and because those are equal, the fractions are equivalent. Method 3 is going to be to rewrite both fractions with the common denominator. So I'm going to get that common multiple this time, and then I'm going to show that those are equal. Two fractions are going to be equal if and only if AD is equal to BC. This is a shortcut. So this is the butterfly method that a lot of people utilize. So I could actually multiply them to figure out if they were equivalent. If I'm ordering rational numbers, so if I'm ordering them, then I know if A, B, C, and D are integers and B and D are positive, then I know that A over B is greater than C over D. So the larger those denominators are getting, the actual smaller the values are becoming. If I want to look at something called denseness, this is a very short concept in what we're learning this week. The denseness is the rational number that is between two rational values. So if I look at 7 over 18 and 1/2, there is a rational number between those two values. So because 1/2 would be 9 over 18 when I got that common denominator, then I was given 7 over 18. Well, what's between 7 over 18 and 9 over 18? Well, 8 over 18. So 8 over 18, or I could reduce that to 4 over 9, is going to be between those two values. So basically, to find the denseness, you want to get a common denominator so that you can compare two fractions with the same denominator, and you're going to find the number between them. Here's the rest of that example, and I'm setting it up. Here, this is an example that we're not going to see a whole lot of, but it is a sequence that I'm looking at. And I'm looking at the sequence where they're generating the values as n over n plus 1. So I'm taking every term and I'm plugging in the value for n, and the denominator is just 1 greater. So that if I was looking at the next term, it would be n plus 1 over n plus 2. So I would need to show that this statement, that n plus 1 over n plus 2 is always greater, saying that I'm looking at increasingly large things. So the inequality would be true, and this is just a proof that I'm doing, not something you have to reproduce in the lab. So I look at this and I say the sequence is increasing because when I factor it out, it is true that n squared plus 2n plus 1 is greater than n squared plus 2n. That's a proof, not a problem for the lab.